Integration by parts is a way to integrate functions that are products, but not like what we've seen before. Recall that for an integral like the integral of x times the cosine of x squared dx, we can use the substitution rule. That is, we can say that u is equal to x squared, and so that du is equal to 2x dx. Based on that, we could multiply and divide in the integrand, so we have 1/2 times the integral of 2x cosine of x squared dx. And then within the integrand, the 2x dx is effectively our du. We would then integrate the cosine and end up with 1/2 times the sine of x squared plus our constant. That was an example of a product, but one of the factors of which was related to a du for a substitution. However, the integral of the simpler function, x times the cosine of x dx, cannot be integrated using previous techniques. This is where integration by parts is going to come into play. Before we see how to integrate this, though, let's look at the integration by parts formula. So I'm just going to say, stay tuned. The integration by parts formula begins with the idea of the product rule. So let's recall the product rule for differentiation. Using Leibniz notation and function notation, the derivative with respect to x of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. Integrating with respect to x gives that the integral of the product of f and g dx is equal to the integral of f prime g dx plus the integral of f g prime dx. Remembering that every integral needs a differential. Because of the first fundamental theorem of calculus, we know that the integral and the derivative offset each other. And so on the left-hand side, we're left with just the product f of x times g of x. And on the right-hand side, there's nothing to do but write down the integrals the way they are. And so we have the integral of f prime of x g of x dx plus the integral of f of x times g prime of x dx. As what's essentially an arbitrary choice, but to really fit what you'll see in textbooks or if you look for this online, I'm going to solve for the second of these integrals, the integral of f of x g prime of x, by subtracting. So we get the integral of f of x times g prime of x dx is equal to f of x times g of x plus, nope, that's a minus, we subtracted, the integral of f prime of x g of x dx. If we let now f of x be replaced by u and g of x be replaced by v, then f prime of x dx will be du, and g prime of x dx can be written as dv. And then this formula becomes the integral of u dv is equal to u times v minus the integral of v du. It's just an easier way to write what we came up with. This is the integration by parts formula. Having seen that, let's go back to the function that I said we couldn't integrate using previous techniques. That would be the integral of x times the cosine of x dx. In order to see how we're going to use the integration by parts formula for this, let's talk about it a little bit. The integration by parts formula has the integral of u times dv, so that's a product of functions. And our task is going to be to identify one function as u and the other function as dv. We'll include the differential with dv, of course. Once I know what u is, then I can start to flesh out the right-hand side of the equation. So the left-hand side is the original integral that we're presented with, and using it, we flesh out the right-hand side. So once I have u, I will differentiate, and then I will know what du is. I can also write what u is in the product of u times v, right? And then once I have dv, by anti-differentiating, I'll be able to identify what v is. And so I can use what's in the integral, u and dv, to express what's on the right-hand side, u times v minus the integral of v du. In the case of x times the cosine of x dx, I'm going to identify x as u, and that will leave the cosine of x dx as dv. We need to account for everything in the original integrand when making our substitutions. We'll talk a little bit later about how I knew to let x be u and not the cosine of x be u, but for now let's just see how this process plays out. If u is equal to x, then du is equal to dx. For the dv portion, if dv is identified as the cosine of x dx, then it follows that v is equal to the sine of x. Now, just as a reminder, the formula is the integral of u dv is equal to u times v minus the integral of v du. And I've noticed I was a little sloppy with my v right then, so I'm going to fix it a little bit. You'll notice every time I write a u, it's got a tail, because sometimes my v's get a little bit sloppy. Some folks have a u and a v that look identical to each other, and I need that not to be the case. We need to differentiate, not calculus differentiate, but we need to distinguish between the symbols that we're using for u and v if we're going to follow our own work, but also if your reader, i.e. me when I'm grading tests, can follow your work as well. Now, the integral of u dv we started out with was the integral of x times the cosine of x dx. And according to the formula, that's going to be u times v, and so x times the sine of x minus the integral of v du. And so it's the integral of the sine of x dx. Now we may look at this and say, well, we started out with one integral, but now we have this x times the sine of x minus a whole nother integral. This isn't getting any better. But if we look at the integrand, it's the integral of the sine of x dx. That's something we can actually integrate. And so that's going to be our final step. The integral of x times the cosine of x dx is equal to x times the sine of x plus the cosine of x plus our constant. See, when we integrated the negative of the sine of x dx, that integrates to the cosine of x. And now we have a value or an expression for the original integral. We have integrated what we were after, and so we do have an answer. Don't forget, though, that we do need a constant of integration. So this is how the integration by parts formula is used. We can even check what we have by differentiating. The derivative with respect to x of x times the sine of x plus the cosine of x. I'll throw in plus c, even though the derivative is going to be 0 for that one. Folks, if we differentiate x times the sine of x, we're going to use the product rule, and so we have the sine of x minus, plus x times the cosine of x, right? So that's u prime v plus uv prime. And then the derivative of the cosine of x is negative sine of x. The sines of x subtract out, and we end up with x times the cosine of x. Therefore, if we differentiate what we ended up with, we do end up with our original integrand. Let's recap this process. First, what we do is we identify u and dv. And that's a choice that we make. Using those u and dv, we find du by differentiating and v by anti-differentiating, and then flesh out the formula. I will make one note here. Never identify dv as the natural log of x dx. It just won't get you anywhere. You can try it, but I warned you. Now, back up here, we identified u as x and dv was cosine of x. But what if we had switched it the other way around? What if we had picked u as the cosine of x? Then du is the negative sine of x dx, no big deal. dv would be x dx, and so v would be 1/2 x squared. So far, so good. Then using the integration by parts formula, I would write down u times v, and so 1/2 x squared times the cosine of x minus the integral of v du. Du has a negative sign, so this would become plus. Well, that's even better. 1/2 x squared times the sine of x dx. Now, we still have this integral on the right-hand side, but if we compare the integral on the right-hand side with what we started out with on the left-hand side, we had the integral of x times the cosine of x dx. Now we have product plus the integral of 1/2 x squared times the sine of x dx. This is now a more complicated integrand. We've made it worse. In general, we want to pick u and dv so that the new integral is not more complicated. There may be exceptions, but this should be a guiding principle that we use in identifying u and dv.